Okay, welcome everyone. Today we are very happy to have our own Marvin, who kindly agreed to present today. And he's going to tell us about the symmetry topics.
Thanks. Yeah, I'd like to thank my fellow co-organizers, as well as Matthew Donaldson for giving me the obligation, the opportunity to speak. And yeah, today about what we're calling the Symmetry Taco, which the newest addition to this kind of food-related terminology that's appeared in this field recently. So this was work posted in the archive last year with Raman here in the audience, as well as with Xie, David, and Abhinav. Okay, so I'll just jump right in. I'll start with like a brief overview of this general area, the SymTFT, and review how it's been used to understand, well, I guess give a new perspective on gap phases as well as gapless phases. Then I'll move on to introduce very briefly mixed states, which is another setting that we'll be discussing in the talk. And I'll the core of the talk will be relating these gapless SPTs to certain gapped and mixed state counterparts, which we'll do using this SymTFT framework that I'll introduce. And finally, I'll talk about what we call an application of this SymTFT, which allows for gauging perspective on how to gauge these symmetries that we'll talk about. Okay. So one might view this SymTFT perspective as a kind of coalescence of various kinds of bulk boundary correspondences. And this concept was sort of introduced to condensed matter physics through this example of the topological insulator, where we have some three-dimensional material which is gapped, and it's sort of looks totally trivial in the bulk, but nevertheless it hosts very unusual boundary phenomena. So in the case of the topological insulator, the boundary hosts a single Dirac cone, which is sort of impossible for any two-dimensional material with symmetries of time reversal and charge conservation. And so the bulk boundary correspondence has been kind of intensely studied and generalized. One kind of very mathematical generalization is of this flavor here on the right-hand side, which is that if I have some bulk topological order, this can be described by some mathematical object called a modular tensor category. This is sort of in correspondence with certain properties of the boundary algebra. So by boundary algebra, it's like another mathematical object which describes what are the local operators that you're allowed to talk about. And so these look pretty different, but they're ultimately realizations of this very general idea that the bulk and the boundary, their properties are kind of one fixes the other in a very in a broad sense. So today, the type of bulk boundary correspondence will not be quite as sophisticated as this highly mathematical one I was talking about. There's a kind of simpler realization of this bulk boundary correspondence, which I'm not sure when exactly this was pointed out explicitly, but one might imagine that somebody realized this as early as, say, 2011 or so. And this is the kind of observation that gap boundaries of G gauge theories in 2+1 dimensions, so that's this D of G topological order. Gap boundaries of this topological order are in one-to-one correspondence with 1D spin chains. So if I have a one-dimensional spin chain with a G symmetry, one could label all of the gap phases by these two elements, these two ingredients. So all I need to do is specify a subgroup H of G. So I imagine I've spontaneously broken down to this subgroup. And then I need to specify a cocycle in the second cohomology class. And this will label kind of the projective representation that this SPT carries. Okay, so it turns out that both of these two objects are characterized by the same type of mathematical object. And this will be kind of part of the goal of this review in the first part of the talk will be to make this kind of transparent, why this should be the case. And in the rest of the talk, I'll kind of get to this other type of bulk boundary correspondence for mixed states. And in this case, it will be that patterns of anion condensation in this 2+1D topological order, this G gauge theory, will be in correspondence, one-to-one correspondence with mixed states, with mixed state phases of 1D G symmetric spin chains. Okay, so let me just review a little bit of this picture that makes this bulk boundary correspondence on the previous slide manifest. So yeah, this can be a very mathematically dense topic, but personally, a picture is worth 1,000 words. So I think it's kind of enlightening to just recast this in very basic, very elementary language. So the goal, one might say, of this SymTFT picture is to kind of extract what the universal data of a 1D lattice model is. And the claim of this SymTFT picture is that the universal data of 1+1D G symmetric spin chain is encoded in the properties of a two-dimensional topological order. And yeah, here I'll just focus mostly on the gap setting where this is the most, there's no kind of loose ends hiding anywhere. So of course, for a 1D lattice model, I'm thinking of a spin chain, perhaps like with a qubit degree of freedom on each side. And I want to focus on the case where there's a symmetry. So the simplest case would just be a Z2 symmetry, which acts as spin flips on each side. And the way to encode this in a two-dimensional topological order is via this appropriately named sandwich construction. So the 1D lattice model is viewed as a thin slab of a two-dimensional topological order. The bulk is the inner part of the sandwich, and the top and bottom are determined by a boundary condition of the topological order. So importantly, we'll fix the bottom boundary. We'll just specify by fiat that the bottom boundary is it's called the symmetry boundary, but it's the charge condensed boundary. So this exists for any symmetry. I can always spontaneously break the symmetry at the lower boundary.
Wait, 1D lattice model, do you mean Ising model or Heisenberg model, quantum or classical?
Quantum. So I
Okay.
think
We could. Z2 is both same.
sorry, I mean quantum, but I just mean I only want to
The Ising model.
yeah, I just want Ising symmetry. Yeah. I forgot to emphasize. Although you can see that the Z2 symmetry specifies what the bulk topological order is. It'll be the Z2 gauge theory, and so the data of the symmetry is sort of isolated at the lower boundary, and all of the dynamics in it will be encoded in the dynamical boundary in a way that we'll see in a second. Okay, so this is how a 1D lattice model, you can kind of thicken it, fatten it, and turn it into this 2D sandwich. So let's just see how this thickening, the sandwich, kind of captures the universal data that we're looking for. So in the simplest Hamiltonian, which respects this Z2 symmetry, I I claim that this is the same as having M condensed on the dynamical boundary. So just as a quick review, the Z2 gauge theory can have two different kinds of gapped boundary conditions, one where E is condensed on the boundary and the other where M is condensed. We're fixing E to be condensed on the bottom boundary. And so the top boundary, which is the dynamical boundary, I'll be varying it as I wish. So in this case, for this paramagnet Hamiltonian, all I'm doing is condensing M at the top boundary. And we know that this Hamiltonian has a unique ground state. And in this kind of SymTFT language, we see this because the Z2 Torah code has a unique ground state with these specified boundary conditions. Okay, it's a fancy way of saying what we already know. The other Hamiltonian that one would consider is this ferromagnet Hamiltonian. And in this case, recall that the bottom boundary we fixed to be E condensed, and now the top boundary we can choose to be E condensed boundary. And to see that it has the correct ground state degeneracy, we can observe that in the gauge theory, there's a line operator which connects the top and bottom boundaries, which anti-commutes with the M kind of string operator. And this leads to a ground state degeneracy of 2, which we of course know from the ferromagnet. It's just the two degenerate ground states ferromagnet. So this is kind of the coarsest piece of universal data in a gap phase, which is how many states are there, is kind of correctly reproduced by this sandwich picture.
Can you explain again the algorithm for the lower boundary you just fix to be something throughout your, and then the upper boundary you just kind of scan possibilities and match the ones that
you scan the possible gap boundary conditions, and those will kind of label the phases. So here this is the example where there's only two options. But in general, when you scan over all of the boundary conditions, you kind of scan over all possible 1D kind of phases with this symmetry.
Mm-hmm. And is there a way to guess which one will be which, or?
Yes, there's an algorithm. I probably won't really get into it, but there's a way to see. Yeah. Okay, so the other kind of universal data in these simple spin chains is the order parameter. So in the case where, again, we're in this paramagnet Hamiltonian, there's a there's a string order parameter, which is just the fact that, if I take the X operator, and I apply it to a line, at least in this fixed point state, I'll get, it acts as 1 on the state. And here, so I'm making, you can kind of just pictorially see this if you identify, the M lines with X's, so you can kind of just read off from this picture that this has the right ground state expectation value. And similarly, in the E condensed, or in this ferromagnet phase, you can similarly read off what the order parameter is. So in the E condensed phase, I imagine I'm allowed to kind of take an E and move it to nucleate E's from the top and bottom boundaries and reconnect them like this. And then this tells you that this Z operator is long range correlated, as one knows from the paragraph. Okay, so in the case of symmetry breaking, these are kind of the only pieces of universal data. But in 1D, there's kind of slightly more complicated things that can happen. And so here I'll use the kind of example, the paradigmatic example of the cluster state to illustrate this slightly more complicated thing that can happen. So the cluster state is an example of a state with a Z2 times Z2 symmetry. So one might imagine there's 2 qubits per unit cell, and there's correspondingly 2 spin flip symmetries. Here's the Hamiltonian. It's not really that important what it is. But following the recipe that I've tried to outline, since we have 2 distinct Z2 symmetries, I want to have a bulk that has a Z2 times Z2 gauge theory. And once again, the bottom boundary will be completely all of the charges, the gauge theory will be condensed. And then I pick the dynamical boundary, this top boundary, to match this Hamiltonian that I want. And yeah, once again, you can kind of eyeball, because in the Hamiltonian I have some combination of z, z's, and x that translates to some combinations of e's and m that you can kind of read off from the Hamiltonian. So the claim is that this dynamical boundary condition encodes the universal physics of the cluster state. So yeah, I won't go into everything, but you can see most of what's going on just from this from the order parameter. The fact that I have this EAMB combination and EBMA combination that's condensed on this top boundary means that I can kind of nucleate to EBMA and kind of pair it up in this way. And what if you kind of use this E M and X and Z dictionary, you can kind of read off that this means that there exists this string order parameter which has long range order in the ground state. And the key physics of the cluster state really is that the endpoint of the string operator carries charge under its own symmetry, and that's sort of what leads to this being a non-trivial SPT. And so going back to this bulk boundary correspondence, once we fix one of the boundaries, we find that the possibilities of the other boundary label all possible 1D ground states. And it was shown in these kind of earlier papers studying gap boundaries of gauge theory that these gap boundaries are classified by a subgroup as well as a cocycle. So that's sort of the reason that this is sort of the pictorial reason why these things should be related to each other. Okay, so with the gap story kind of in place, let me move on to a particular kind of gapless phase called gapless SPTs, and let me describe their anatomy. So once again, I'm still in this one-dimensional spin chain setting, and now I'm imagining I have a Z4 symmetric spin chain. But let me assert that the dynamics are such that that I kind of restrict myself to a low energy subspace, such that the Z2 subgroup of the Z4 acts trivially. Okay, so maybe I imagine I put some constraints so that at low energies I only have this Z2 symmetry acting trivially. So yeah, if this Z4 symmetry is the full symmetry group, but in my low energy subspace, the Z2 subgroup acts trivially. What that means is that in this low energy subspace, my Z4 symmetry actually acts as a quotient. So this G low would be the symmetry group that acts on the low energy subspace. And it can be the case that this G low, the low energy symmetry group, can be anomalous, even when there's nothing funny about the full symmetry group. And so if you kind of engineer your system in this way, that means that your low energy theory could be forced to be gapless if you want it to be symmetry preserving.
You said anomalies. What do you mean?
So here, let's see.
There's so many meaning.
Yeah. So here by anomalous, I mean it's an obstruction to gauging the symmetry. So if I only have a for example, this Z2 symmetry at low energies, I can't couple it to dynamical Z2 gauge fields. That's sort of what I mean in this context. And in particular, this means that a symmetric gap phase is forbidden. So you could also take that as the definition. Okay, so what can this SymTFT picture say about this situation? So once again, we want to be in this, since I'm considering a spin chain that has a Z4 symmetry, I want my bulk 2 plus 1D theory to have a Z4, to be a Z4 gauge theory, so the Z4 toric code. And once again, you know, I'm fixing the symmetry, the bottom boundary to be the boundary condition where E is condensed. So how do I capture this kind of this symmetry structure of the gapless SPT? So the idea is that this kind of enforcing that the low energy in the low energy there's a Z2 subgroup that acts trivially. The way to enforce that is by doing some kind of partial anion condensation. So instead of condensing a full instead of condensing anions such that, you know, the entire theory is totally trivialized, I'm going to condense some smaller amount of anions that leaves some topological order left over after condensing. And so in this case, the correct thing to do is to condense this E squared M squared anion. And the leftover topological order after this condensation is this so-called twisted Z2 gauge theory. Which also goes by the name double semyon. So how is this implementing the correct thing? So here's one way to see it. If I act with when I act with the symmetry, the Z2 subgroup of the Z4, so the symmetry operators are always kind of M lines. So when I act with M squared, I can pull an E squared from the bottom boundary, combine it with this M squared, and then kind of annihilate it at this boundary where E squared M squared is condensed. So yeah, in this picture, you can see that that M squared acts as the identity in this low energy. And furthermore, you can see that it's not so in going from this picture to this picture, I've kind of just pushed I've pushed this boundary where E squared M squared is condensed, and this empty boundary. I've sort of pushed them together to get this picture. And from this picture, you can just read off the fact that there's this non-trivial string order parameter. And so this tells you that in this gapless SPT, you'll have this particular type of string order.
Why do you call it gapless SPT? Or why does one call it? I mean, maybe it's not your fault,
Yeah.
but
Yeah, it's not my fault for sure. I think this is the reason why this gapless SPT is a reasonable name. It's because it has this string order, and also the endpoint of the string order parameter is carries charge under the symmetry as well. So this is like the canonical thing that happens in 1D SPTs. And so I guess it's also, in this case, it's also important to note that this kind of pattern of string order is impossible to realize in purely in a gapped system. So you know, there's some kind of like symmetry fractionalization that one can see from the endpoint of the string order parameter, but it can't happen in a gapped system. So
it can't happen in a gap system, or it can't happen in a gap system that realizes the Z2 linearly. If you spontaneously break the Z2, you'll probably do it. Right?
Spontaneously break the Z2.
You have Z2 with some, you know, non-trivial F symbol. What if I just have multiple ground states? I can always do a symmetry extension and realize.
I think what I'm trying to say is you can't realize this pattern of symmetry fractionalization if you have a Z4 symmetric system. You know, if you have Z4 symmetry and your system is gapped, you will not have this
But why
gap
would
that you need.
yeah, unique, but
yeah.
But if you spontaneously break
Yeah,
then
that's
it's
right. Yeah. Good. Okay. So now I'll move to the other setting, which we'll try to apply this framework to, which is that of mixed states. So in mixed states, what we're studying rather than just rather than a state are density matrices. But there's this cute trick that you can just play, which is just to view a density matrix as being itself a state in a doubled Hilbert space. So if I take the broad Ket Hilbert space and I tensor them together, I'm just viewing my density matrix as a state in this bigger Hilbert space. And so obviously this is very useful in porting over our intuitions about pure states over to this setting. But obviously we have to be a little bit careful because not every state in the doubled Hilbert space will correspond to an actual density matrix. So the constraints, of course, are that density matrices, they have to be Hermitian, they have to be positive. And so we'll get back to these constraints in a bit. But nevertheless, it's a useful kind of thing to keep in mind that we can just view density matrices in this way. So one way of obtaining density matrices is by subjecting a pure state to some kind of incoherent noise, or errors, as one might call them in the. And so if we apply noise to a pure state, this corresponds to, well, if we apply noise to a topological order, a pure state topological order, what this corresponds to in this doubled state picture is a pattern of anion condensation in this doubled topological order.
Can you say more technically what you mean by operator E? What actually is that?
So E could be something like, for example, with 50% probability, apply an X operator at a particular link, and with 50% probability, do nothing. So that's a kind of error channel that is.
So the output is another density matrix?
The output is a density matrix. Yeah. So I'm imagining I start with a pure state, I apply this kind of channel, and I get out a density matrix. And which density matrix, in this case, and sort of in a broad class of cases, the density matrix that you get out is if you take the original density matrix, view it as a state, and then kind of condense anions in this doubled state. And the anions that are condensed will be kind of this form, A plus, A minus bar, where plus and minus labels the broad Ket, and A and A bar label the inverse.
So are you imagining that this still kind of doesn't leave the ground state manifold? Doesn't excite your system?
No, it will leave it'll leave the ground state manifold. Yeah.
Okay, but probably you don't want to leave it by too far. I mean, you don't want to create a thermal state, or.
So this is kind of like a thermal state. Yeah, this is kind of like an infinite temperature state in one of the anions.
But the anion condensation of applied to a topological order will be another topological order.
Yes. So yes, that's right. So it's an infinite temperature state of one of the anions and a zero temperature state of the other anion. So for example, yeah, I'm imagining a situation where like I start with the Tor code, and for example, I could apply errors that kind of like proliferate, the E anion, but leave the M anion totally invariant. So from the perspective of the E anions, it's like an infinite temperature state, and from the perspective of the M anion. Yeah.
The X's there, the red insertions, they're operators that implement the operation E.
Yes, they're channels that implements. Yeah, you can think of E as applying these channels, global channels to the state. Okay, so the ingredients of the extra ingredient that a mixed state that buys you is that, well, you're working in this kind of doubled bigger this doubled Hilbert space, and so that comes along with an extra notion of symmetry that's not there or that's not important in pure states. So conventionally we learn in quantum mechanics that symmetries act on density matrices in this way on the right. So we'll conjugate a density matrix by some symmetry operator, and it leaves the density matrix invariant. But there's a kind of stronger notion of a symmetry in mixed states where I could just act with the symmetry on the left-hand side, on one of the sides of the density matrix, and maybe it leaves the density matrix invariant up to the phase.
Perfect location.
That's a good point. So why is this still a density matrix?
Yeah. Yeah, so that's right. So the strong symmetry may not turn a density matrix into a density matrix. It could turn it into a density matrix up to a phase. That's yeah. On the other hand, if I have some if I act with a density matrix on the right and left by conjugation, this will always be another density matrix, whether or not it's the same as the original. So yeah, acting with the symmetry just on one side, it may not leave it may not turn the density matrix into a density matrix, but nevertheless, it's still a useful kind of operation to do on a density matrix. And so in this doubled kind of picture, they have these nice representations where a strong symmetry just acts on one copy of the Braun-Cat-Hilbert space, and a weak symmetry, since it acts by conjugation, it acts on both the right and left. So it'll act on both copies of the density of the Cat-Hilbert space.
Are those anions condensed along the top of the picture?
Yes. Okay, that probably doesn't make that much sense right now, but hopefully it'll make sense in a little bit. Yeah. Yeah. Okay. So now I'll talk about how this SymTFT picture for gapless states is related to those of gapped SPTs. I should say gapped and mixed SPTs here. Okay, so here's the setup. If we recall from our discussion of gapless SPTs that we can understand this like SymTFT picture by condensing some subset of the anions. Maybe not all of the anions, just some of them. Okay, so now I'll imagine I start from some big blob of topological order, this G gauge theory. And I'll condense, some subset of anions in this middle region. So I obtain like this sequence of domain walls between DG, this DG with some anions condensed, and DG at the top again. So now I can do two things. One is I can cut this picture along the middle and obtain this picture, which may remind you of the kind of SymTFT picture that we drew in the case of a gapless SPT. Now, on the other hand, we can do this. We can fold this picture in half and obtain this type of bilayer system, this DG times DG bar system, and this will look like well. So first, if I think of this as a G times G, so yeah, DG times DG bar is the same as G times G gauge theory. And so since this top boundary here, is a gap boundary, this will correspond to some one-dimensional G times G SPT.
This does not seem to be the most general way to obtain that kind of DG times DG bar symmetry in bulk. You could have had two different algebras and interfaces between them, and you could have made that picture more complicated. This is like some very special one.
Yeah. So indeed, this will not give you all possible boundaries of G times G gauge theory. So this will give you some subset of gap boundaries. Right. And it's this subset of G times G SPTs that will sort of be in correspondence with gapless SPTs. And this subset of G times G SPTs are ones that kind of one should also naturally think of as being G mixed state SPTs for reasons we'll see in a second. So just to illustrate, using the kind of gapless SPT example from earlier, we could start with the Z4 toric code on the top and bottom, and condense this E squared M squared anion in the middle, and then fold it in half in this way. And if we kind of enumerate what are the anions that are condensed at this top boundary, we could enumerate them and list them out. And this will be some gap boundary of the Z4 times Z4 toric code. One thing to see immediately is that in these set of anions that are condensed, one of the anions is this E squared anion. And since I've condensed, and this is a pure charge, so since I'm condensing a charge, that means I've spontaneously broken some of the symmetries. And in this case, you can kind of convince yourself that this is spontaneous symmetry breaking to this particular subgroup of Z4 times Z4. So it's the Z4 diagonal subgroup, and as well as a Z2 kind of anti-diagonal, or Z2 just acting on a single copy of. And you can play the same game as before. In fact, I'll play it right now, of looking for string order parameters in this SPT. So yeah, because we have E squared M squared, being condensed at the top boundary, we have this similar string order parameter as before. One kind of one other ingredient is you also obtain this other string order parameter, which involves both A and B copies kind of together. So you can read off the string order parameters in this case as well. Okay, so yeah, let me comment on Clay's earlier. What Clay pointed out earlier is that we don't get all possible kind of gap boundaries of G times G gauge theory in this way. So what do we get? So let me try to characterize what are the possible kinds of anion condensation that occur at this top boundary. So let me define this matrix W with indices anions in DG and anions in GG after condensation. So I'll just define this matrix to be 1 if an anion A turns into alpha when I tunnel through, and 0 otherwise.
It would not in general be a unique fusion channel, right?
Not in general. Yeah. So
So
here,
what is W if A can turn into alpha 1 through alpha 10?
so W will be the multiplicity of possibility that A turns into alpha 1 or alpha 2. Okay, so that's what's happening on the left-hand side. Yeah, I'm imagining if I have an anion A in here and it tunnels to alpha there, then this matrix is 1 and 0 otherwise. And if there's some fusion multiplicity, that you can also put that in there. Okay, on this right-hand side, let me for simplicity, let me kind of first talk about the abelian case. So we'll define a different matrix M. This will be M A B bar to be 1 if this combination A1 B2 bar is condensed on the boundary, and 0 if not. So here I'm imagining A on the one layer and B on the other layer. If they kind of meet up and kind of annihilate each other at the top boundary, then this matrix element is 1. Okay, but importantly, we know because of this folding trick that for anions in this intermediate topological order, they will only, if I take an anion alpha and I kind of just move it over because all I've done is fold, alpha will turn into alpha bar when I go across this boundary. So we know that this in terms of the anyons at this in this intermediate topological order, this matrix is just the diagonal matrix. And so what we can show is that, or what you convince yourself is that this matrix of anyons condensed at the top boundary will just be, you know, if I have an anion A, I tunnel through it, turns into alpha. If I have an anion B, it tunnels through it, turns into beta. These things can only condense if alpha and beta are the orientation reversals of each other. And so this M will be this this combination W times W transpose. And so what this tells you is that this condensation matrix in this folded setting will be both symmetric and positive. And so this is what lets you identify these folded SPTs with mixed state SPTs. So I haven't shown that this is the case, but it should be kind of hopefully very reasonable that this constraint that comes from folding is the same constraint that arises from hermiticity and positivity of density matrices. So in fact, we can show at least in the abelian case, that anion condensation that satisfies hermiticity and positivity will be symmetric and positive. Like the anion condensation matrix will be symmetric and positive.
Should I say one more time? What is the general definition of the anion condensation matrix?
Yeah. So hereby anion condensation matrix I'm referring to as N. So for a bilayer system, N is like, you know, so N really I should not really think of as a matrix. It's just which anions are condensed at the top boundary.
Yes.
But because I'm in this bilayer system, you know, this thing has two indices, so it kind of looks like a matrix. And it's useful to think of it as a matrix because if I view it as a matrix, it's positive. It's positive definitely. But really, it's like a, you know, it's just the thing that takes an anion as a. It's just saying which anions in the topological order are contained in the top boundary.
I'm just confused because the answer to that question is usually some more complicated algebraic structure, not a matrix.
Oh yeah, okay, yeah. In the more general case,
It's like the whole algebra with its own fusion rules and so forth like that.
Yeah,
I didn't know you could package it into some matrix.
no, you can't. Yeah. So this is strictly speaking the matrix. This matrix has all the data in the abelian case, and it has some of the data in the non-abelian case. So in the non-abelian case, yeah, I would say, yeah, we don't have proof that this thing, we don't have proof that you know all the correspondences work out in the non-abelian case.
And then on the next slide, what is the relationship between M and the density matrix? I mean, why should I want this M to be Hermitian and positive? Right, so far it's just to me. I so far see like a free association. I have like a rho is supposed to be Hermitian and positive.
Yeah.
And now we have an M that's Hermitian and positive. But what is the relation between M and rho?
So yeah, so there's two there's kind of two different rows, right? So one is the row of the bulk, and one is the row, you know, of the boundary that's determined by this pattern of anion condensation at the boundary. So the statement is that so first the bulk topological order, if in this doubled space, it's a valid density matrix if this M matrix is so rho in the doubled space will be a valid density matrix if this M kind of matrix is symmetrically positive. And the other statement is that
the density matrix in which space? Like you're working in the ground state space of the topological order when you say that? Like It's just the density matrix of the finite dimensional space of ground states, or will we have more?
So
to that?
yeah, sorry, I should say, so if I view this as a state in the doubled space, this state in the doubled space will correspond to a valid density matrix in the kind of original of the original system. If this anyon condensation matrix is
So the ground state is degenerate.
yes, yeah.
So when you say density matrix, you mean the space of states should be, it's the size of the matrix. If it is not degenerate, then there is
For simplicity, let me
matrix.
yeah, for simplicity, let me think of it as being yeah. So implicitly, I have in mind that geometry is a cylinder, is a cylinder. So there may or may not be degeneracies based on the boundary conditions. And in fact, yeah, in the case of that I'm thinking about, the boundary conditions will be so that there's no degeneracy. So the degeneracy is not important for the
Density, what is density matrix? It's a matrix, right?
yes.
How big is a matrix? It's a number of states. So dimension of this space of states.
So you mean what
Dimension of the matrix. So you have to have, to talk about density matrix, you have to have many states.
Yeah, you're going beyond the ground state, right? I think.
Yeah,
you
yeah,
mentioned this.
going beyond the ground
So
state.
it's one number, or it's
So are you asking like how big is the space? Like, the density matrix is some n by n matrix. What is n? That's what you're asking. Yeah, I
if the
mean,
ground state is not degenerate and you are in the ground state, then n is one, right? So it's not a matrix.
I think he's going beyond the ground state.
yeah.
That's what
that's
I'm
exciting
trying
state.
to,
Yeah.
that's what I'm trying to figure out.
Yeah, so we're going beyond the ground state of the original Hamiltonian. That's
There are tons of.
But does
exciting
the answer depend on how you do that? Right now, you have some very small specification of some kind of symmetry-based specification of what you're doing.
yes.
And you said that this will apply no matter how you embed into any model with G symmetry.
Yeah, how far do you go? I mean, do you have the Higgs boson, in here?
Yeah,
Are you exciting the?
yeah, that's kind of a.
So let me think. Yeah, I guess the setting is, I start from some, implicitly I'm imagining I start from some ground state of Z2 gauge theory. And I on each, with 50% probability on each site, I create a pair of E anyons or not.
But even the notion of site depends on some like microscopic model.
Yeah.
So you have some lattice UV completion in mind, right? You're
I have
not
the
talking
line
about.
UV completion in mind, but I don't think that's important as far as I mean, it's just the same as like a UV completion of Z2 gauge theory. It's not.
I don't know. I mean, it
Gauge
depends,
theory
right?
can be complete on its own.
Sure.
No, let's say I do this in an actual setting. I mean, it might depend on the phase diagram of the model, right? Maybe it enters a completely different phase. Maybe there's new excitations. I mean,
Yeah.
it seems like there's some kind of assumption going in here. That...
Yeah. Okay. We can work in a UV, in a UV completion. On a lattice-based UV completion. That implicitly, I want to be in that context. So
But should it also hold for other models which just have the same symmetry?
yes. Yeah. I mean, I don't have a justification for that, but that's like, that's sort of always what's implicitly happening in these topological things, right? Is that I have some lattice model, but it flows to some TQFT, and then I kind of forget about the lattice. And I guess part of the justification for why we're allowed to do this is that the anion condensation in this kind of doubled picture in this density matrix, the fact that applying certain error channels responds to anion condensation means I can kind of work only in this topological limits. And anion condensation is kind of this universal thing, so I don't need to kind of go back to the lattice necessarily to do that. So yeah, so what I want to convey on this slide is that, you know, in the previous couple of slides, I've mentioned a way to construct a G times G SPT, a G times G SPT out of this folding construction. And what I want to claim is that this will equally give you a mixed state with G symmetry. Okay, and so let me kind of explain the anatomy of this mixed state SPT by analogy with in the gapless case. So again, I'm imagining a situation where I have the symmetry of the system is this C4 group, but a subgroup of this is a strong symmetry. So that means the density matrix can act with it on only one side. That means it leaves the density matrix invariant. So what that means is that every state in this density matrix ensemble is invariant under this Z2 symmetry. And the quotient is what one might want to call this weak symmetry. So this is so this is again just repeating the same kind of picture from earlier, but now with this kind of in this mixed state context. So now the plus and minus denote the Braun-Ket, and condensation of the form E plus squared, E minus squared, for example, is kind of incoherently proliferating this E squared annual. And so from this picture, you can read off these kind of string order parameters once again. And in this case, it's it should be understood as an expectation value in some density matrix. And just as before, there's this other string operator that kind of couples the two layers of the density matrix. And this will be this kind of funny expectation value where there's two copies of the density matrix appearing here. So these kinds of expectation values are much harder to kind of experimentally access than these sort of ordinary expectation values. But nevertheless, these are kind of what the characteristic order parameters of these mixed state SPTs. Okay, in the final few minutes, let me talk about gauging and how this sandwich picture kind of lets you think about gauging in an accessible way. So recall that in this sandwich picture, the bulk is this topological order. We have the boundary that I said was fixed. That's the charge condensed boundary, and the dynamical boundary, in essence, chooses the state or chooses the Hamiltonian. But and now let me say I want to gauge the some subgroup of this Z2 times Z2. Let me pick the diagonal subgroup. So the way to gauge in this in the sandwich picture is to change this symmetry boundary condition that I said was fixed the whole time. And what do we change it to? So if I want to gauge the diagonal Z2 symmetry, what I want to change this boundary condition to is the boundary that, if this were here, this state would correspond to SSB to the diagonal Z2 sum. So that's how I choose this boundary condition to be gauging. So if I want to gauge a H subgroup of G, I modify the symmetry boundary to the dynamical boundary, which would be the SSB to H. So to see how this works, we can see how the symmetry operators kind of transform under this gauging operation. So when in the original situation, when the symmetry boundary consists of E condensed, my symmetry operators, the things that influence the symmetry will be the M lines. But once I've gauged the Z2 symmetry, I've replaced the bottom boundary with this particular particular combination of anion condensations, we can now see that MA and MB get identified because if I kind of bring MA down to the bottom boundary, it'll become MB. So MA and MB become identified, and so that's what you'd expect when you gauge the diagonal subgroup. And in general, you can read off what the symmetry operators are. They're the lines that are confined at the symmetry boundary, at this bottom boundary. And so the other kind of confined line would be this EA, which is becomes identified with EB. And this is this EA or EB line is now like the dual symmetry after I gauge the diagonals. Okay, so the reason to talk about this is because in this mixed state context, we have both strong and weak symmetries, and you can ask what's the result of gauging the weak symmetry. So this is the exact same setup as before. I had Z2 times Z2, but now the diagonal Z2 subgroup is the subgroup of weak Z2 symmetries. And so if I want to gauge that, once again, I change this bottom boundary to be this particular boundary condition. And something curious happens with this once you do this. So once I change the boundary condition to be this E plus E minus and M plus M minus condensed boundary, so this is the result of gauging the diagonal Z2 symmetry or the weak Z2 symmetry. I can kind of enumerate the possible gapped boundaries at the dynamical boundary condition. And one by one, I can look at all of them and find that all of them, there's some kind of spontaneous symmetry breaking happening in all of them. So in no boundary condition, we put a unique ground state, so to speak, in this doubled space. So yeah, the point is that all of the gap boundaries will break this symmetry. And so this is kind of an anomaly in the sense that there's some obstruction to having a trivial gap ground state in this context. And importantly, this is really only there because we're in this mixed state setting. So if this was just the usual Z2 times Z2 toric code, at this top boundary, I could have E plus M minus and E minus M plus condensed, but that would violate the positivity condition that we impose on the density matrix. So this is really something that's there only in this mixed state context. Okay, so yeah, just to conclude, just develop this folding taco picture that relates gapless SPTs to these mixed state and gapped SPTs. There was some concurrent work that happened around the same time that I encourage people to also check out. I think some interesting kind of open directions are kind of enhancing this bulk boundary correspondence to include these very mathematical the things I mentioned in the introduction. This kind of boundary algebra and bulk topological order correspondence. Another kind of concrete thing that one might wonder about is there a sense of invertible mixed states, and correspondingly would these form some kind of spectrum, and would these be useful in classifying?
Well, just in your examples, where is the obstruction to gauging valued? Is it valued in an abelian group?
I don't know. Yeah, I have no idea. So that was in that example.
But is there some linear structure on the obstruction? Like there's some notion of adding two obstructions together?
I have no idea. Actually, I mean, I think it's similar to in your paper with Carolyn for these non-invertible symmetries.
There I would say there's no linear structure on the on the space of obstructions.
So yeah, the way I understood that was in that case, it's just like you look at the possible gap boundaries and all of them kind of break the symmetry, and you kind of then you say, okay, that's the anomaly. That's sort of all I'm saying in this case as well. So I don't know.
Right, but in the group-like case, you might hope for more.
Yeah.
Right, in the group-like case, there actually is a linear structure.
Right. Yeah. So I don't know what the answer is in this case. Yeah, and then, there might be, I mean, I'm sure there are, but it'd be interesting to work out, continuing topological field theories for both these SPTs in the boundary and these mixed state topological orders in the floor. Be interesting to work out the continuing topological field theories that have all the universal properties. So that's all for me. Thanks.
Didn't quite follow the anomaly, big state anomaly. Can you say again what's the statement there? You have a mixed state in one dimension, in 1+1 dimension. It's some interesting property. What is the property?
So the property is that any kind of zero correlation length state will break one of the symmetries.
Not connect.
State. What's the statement about? You have a 1+1 dimensional state. You have a 1+1 dimensional Hilbert space. What do you have?
I guess I have a 1+1 dimensional density matrix.
Okay.
And but I arrived at this density matrix by gauging the weak symmetry. So yeah, let me start with a density matrix with kind of strong and weak Z2 times Z2 symmetry. And I gauge the diagonal subgroup. And then the claim is that after gauging, there's no there is no symmetry. There is no state that will preserve all of these symmetries of the resulting thing. So in this case, the result. So there's a
No density matrix.
there's no density matrix that will preserve all the symmetries. And by all the symmetries here, I mean, so because I've gauged the diagonal Z2, the kind of symmetry that acts on the right is identified with the one that acts on the left. So that's one of the symmetries. And the other symmetry is the dual symmetry that one gets from gauging. And so, yeah, the claim is that there is no density matrix that will respect both of these symmetries.
So it's a statement about two symmetries. I mean, usually I think of anomalies as a statement about symmetries acting in some Hilbert space. So you have some symmetries.
Yeah. So here it's symmetry acting on space of on density matrices. The fact that kind of it's a symmetry of a density matrix is important. Yeah. And so both of these symmetries will be you could say they're like a strong symmetry mod a weak symmetry, in the sense that they act, you could act with them on one side and it's like equivalent, it's like gauge equivalent to acting with them on the other side.
Any other questions? If not, let's thank Marvin again.
Marvin, I missed it at the very beginning. This is a paper, or is it already out?
Yeah.